This content is produced by Pass the CSLB, an independent audio-first study companion for busy California B general candidates. I build these lessons from official CSLB study guide topics and reputable source-backed California materials, so you can study on the go. This is exam prep reinforcement, not legal, professional, engineering, or job-specific advice. Exam content is set by PSI and the CSLB and may change, so always verify current requirements against official CSLB materials. No exam outcome is guaranteed. Now let's get into it. Concrete, locks, and whatever is underneath it. If the support, moisture control, steel, hardware, safety setup, or inspection status is wrong when the chute opens, the mistake does not disappear. It becomes concealed, harder to verify, and usually more expensive to correct. That is the central field decision in this lesson. A general B contractor has to treat the pre-pour condition as one coordinated system, not as a stack of unrelated trade tasks. The practical question is simple. Is every condition that will be buried by concrete ready to stay buried? I do not mean that the contractor redesigns the foundation in the field. Structural design, soil recommendations, and special details belong to the approved plans, the geotechnical report, and the responsible design professionals. I mean that the contractor verifies the work against those documents, coordinates the trades, protects the crew, obtains the required inspection, and stops the pour when a concealed condition is not ready. Uniform support starts with what is removed, not only with what is added. Vegetation, topsoil, roots, debris, and other foreign material do not belong under a slab. Organic material can decay and leave voids. Loose or irregular fill can compress after the concrete has hardened. The slab then loses uniform support, and cracking or differential movement can follow. The California requirements in this source report place clear limits on unapproved fill beneath a slab. Clean sand or gravel may not exceed 24 inches in depth, and earth fill may not exceed 8 inches, unless deeper fill is approved. Those limits matter because a deep fill condition is not corrected merely by driving over it or hitting the surface with a hand tamper. The fill has to be evaluated, placed, moisture conditioned, and compacted as required by the approved design and soil recommendations. For engineered fill, the report identifies a common minimum of 90% of maximum dry density at optimum moisture content under the modified Proctor method. That number is not a visual guess. A surface can look hard and still hide loose zones below. Field verification, when required, belongs to the qualified inspector and the approved testing process. Imagine a contractor who discovers that a utility trench was backfilled with loose earth just before slab preparation. The tempting decision is to level the top, place aggregate, and keep the schedule moving. The better decision is to stop and compare the depth and material with the approved requirements. If the fill exceeds the prescriptive limit, the contractor needs the required engineered direction, compaction, and verification before covering it. The immediate delay is visible. Settlement beneath a finished slab is the hidden cost that the delay is trying to avoid. I want you to remember the difference between compaction and appearance. Compaction is a measured condition of the soil mass. A smooth surface is only a surface. The moisture control system beneath an interior slab has two separate jobs because ground moisture moves in two different ways. Liquid water can rise through tiny connected pores by capillary action. Water vapor can move from the more humid soil environment toward the drier interior. One layer interrupts liquid movement. Another layer slows vapor movement. The capillary break comes first on the prepared subgrade. The report specifies a 4-inch thick base of 1/2 inch or larger clean aggregate. Clean, relatively large aggregate leaves open spaces that interrupt the small continuous pathways needed for capillary suction. That layer is not the vapor retarder. It handles liquid movement. Above the capillary break, the report requires a minimum 10 mil polyethylene vapor retarder, conforming to ASTM E1745 Class A. The material has to be continuous enough to function as a barrier, which means the details matter. Joints are lapped at least 6 inches. Seams are sealed with approved tape. Pipe and conduit penetrations are sealed so that the barrier is not reduced to a sheet full of openings. The placement rule is easy to confuse if someone learned an older practice. The vapor retarder belongs in direct contact with the concrete slab. I do not place a sand cushion between the retarder and the concrete for the interior slab condition described in this report. A sand layer can hold water between the concrete above and the low permanent sheet below. That hidden moisture can continue moving through the slab and contribute to flooring and adhesive problems later. I put the under slab requirements together in this chart so you can see the sequence as one moisture and support system. Start with approved, uniformly supported subgrade. Respect the fill depth limits. Use engineered compaction and testing when required. Place the 4-inch clean aggregate capillary break. Install the 10 mm Class A vapor retarder. Lap the seam 6 inches. Seal penetrations, and keep the retarder directly against the slab. The central distinction is worth repeating. Aggregate interrupts capillary liquid movement. The vapor retarder controls vapor diffusion. Neither layer substitutes for the other. The slab and reinforcement checkpoints begin with a basic dimensional rule. A concrete slab on ground must be at least 3 1/2 inches thick under the prescriptive requirement in this report. The approved plans may require more. The field supervisor does not turn the minimum into a universal design. I verify the actual project requirement and make sure grade, forms, depressions, and embedded items do not reduce the plate thickness. Reinforcing steel also has to remain where the plans require it, while concrete is moving around it. Rebar, lying on the soil or resting directly on the vapor retarder, does not magically rise into position during the pour. Chairs, dobies, and other approved supports hold the steel at the specified elevation. The supports and ties have to survive foot traffic, hose movement, and placement without allowing the mat or bars to sag. Concrete cover is the distance from the outside surface of the reinforcing steel to the outside surface of the concrete. Cover is protective concrete, not empty clearance. The report gives several inspection values. Concrete cast against and permanently exposed to earth requires 3 inches of cover. Formed concrete exposed to earth or weather requires 2 inches for number 6 bars and larger, and 1 1/2 inches for number 5 bars and smaller. Interior slabs and walls not exposed to weather use 3/4 of an inch for number 11 bars and smaller under the cited table. Why does earth contact need more cover? Soil keeps the concrete exposed to moisture and possible contaminants. If those reach the steel and corrosion begins, the rust expands and can crack or break away the surrounding concrete. More cover creates a longer protective path between the environment and the bar. For continuous footings and stem walls, the report identifies a minimum of 2 longitudinal number 4 bars, one near the top and one near the bottom. That is a prescriptive baseline, not permission to ignore a structural detail calling for additional steel, different bar sizes, laps, hooks, or locations. This chart separates the cover conditions that are commonly mixed up. The largest value belongs to concrete cast directly against earth. The formed and weather-exposed values depend on bar size. The smaller interior value applies only to the stated interior condition. I use the exposure first, then the bar size, then the approved plan. That order keeps the numbers attached to the condition instead of floating around as disconnected facts. A simple field check follows from this. If a footing bar has dropped to the bottom of the trench, the issue is not merely that the bar looks low. The required concrete cover has disappeared. The contractor needs to correct the support before placement, not hope the concrete crew can pull the bar into position while the trench is filling. The foundation to framing connection has its own pre-pour rhythm. The report requires sill or foundation plate anchor bolts with a minimum diameter of 1/2 inch and a minimum embedment of 7 inches into concrete. The maximum spacing is 6 feet on center. Each plate section needs at least 2 bolts. The end bolt is located no more than 12 inches from the end, and no less than 7 bolt diameters from the end or splice. The washer is not an ordinary small round washer. The report specifies a steel plate washer at least 3 inches by 3 inches, by 0.229 inches thick between the sill plate and the nut. That large bearing area is a specific connection detail the field supervisor has to recognize and protect. I use a short memory rhythm for the anchor bolt checkpoint. 7 inches deep, 6 feet apart, 12 inches maximum from the end, and 2 bolts minimum per plate section. Then I add the part that does not fit neatly into the rhythm. 1/2 inch minimum bolt diameter, the minimum distance of 7 bolt diameters from an end or splice, and the 3-inch square plate washer with the specified thickness. Do not let the memory aid replace the plans. Hold downs, shear wall details, special anchorage, edge distances, and engineered connections can add requirements. The value of the memory aid is that it helps you notice an obvious miss before the inspection, such as shallow embedment, a long unbolted plate section, a bolt too far from the end, or missing plate washers. Pre-pour readiness also includes the condition of the work area. Exposed reinforcing steel is not only a structural component. It can be an impalement hazard. The report states that projecting reinforcing steel extending up to 6 feet above grade must be guarded with approved protective covers or troughs when employees are working around or over it. A thin plastic mushroom cap may protect a hand from a scratch, but the source report does not treat that as impalement protection. Manufactured impalement covers must be approved and capable of passing a test using a 250-pound sandbag, dropped from 10 feet. The point is that the cover needs a load-spreading element strong enough to resist penetration. The supervisor has to distinguish a rated protective cover from a bright piece of plastic that only looks protective. Formwork has to be securely anchored, guyed, or braced against collapse. Reinforcing steel must not be used as a guy or brace for frame panels or concrete forms. Steel that belongs to the concrete assembly is not a substitute for a designed and secure form bracing system. Suppose a crew drives short rebar stakes beside a footing form and leaves the ends exposed because they rise only a foot or two above grade. The hazard is still at the height where a worker can fall onto it. The correct field response is to guard the projection with approved impalement protection and keep the walking and material handling area controlled. Shorter does not mean harmless. Concrete delivery adds a clock to the operation. The report cites the ready-mix concrete limit as 90 minutes or 300 drum revolutions after water is added to the cement and aggregates, whichever comes first. I think of it as 2 clocks running at once. The time clock and the revolution clock do not negotiate with each other. Concrete hardens through hydration, a chemical reaction that begins when water contacts cement. As time and mixing continue, the mixture loses slump and becomes harder to place. The dangerous shortcut is to treat an old, stiff load as a workability problem that can always be solved by adding water. Uncontrolled water changes the water-to-cement relationship and can reduce strength and durability. The field supervisor should check the batch ticket, arrival time, revolution information, approved mix requirements, and project procedures before discharge. If a load is outside the permitted limit or its condition is questionable, I stop placement and resolve it through the responsible supplier and project requirements. I do not let schedule pressure turn an expired or unverified load into concealed concrete. This is also why the site has to be truly ready before the trucks are dispatched. A missing inspection, unfinished penetration seal, or collapsed rebar support can leave a mixer waiting while both clocks continue to run. Inspection sequencing is the final control before concrete hides the work. For a foundation inspection, the trenches are excavated, forms are erected, and reinforcing steel is tied and in place before the inspection. Concrete is placed only after the required inspection is completed and approval is obtained. For a slab or underfloor inspection, the in-slab building services, conduit, piping accessories, and vapor retarder are installed before inspection. Again, concrete comes afterward. The contractor has to coordinate plumbing, electrical, reinforcement, moisture control, forms, hardware, and access so the inspector can actually see the work that is being approved. This sequence chart puts the pre-pour decision in order. First, confirm the subgrade, fill, and compaction requirements. Next, complete under-slab services and the capillary break. Then install and seal the vapor retarder. Set forms, reinforcement, anchor hardware, and required supports. Correct impalement and form bracing hazards. Obtain the required inspection and approval. Only then release concrete for placement and monitor the delivery limit. Imagine the opposite sequence. The concrete crew arrives while a plumber is still sealing penetrations, a bolt line is incomplete, and the inspector has not approved the work. Every minute of delay consumes delivery time, and every rushed correction creates another opportunity to puncture the barrier or move the steel. Good supervision protects quality by moving those decisions earlier. My final pre-pour check is built around one sentence. If concrete will conceal it, verify it before concrete arrives. I look below the slab for uniform support. I look at the moisture system for the correct aggregate, material, laps, seals, and direct contact. I look at the steel for size, location, support, and cover. I look at the anchorage for embedment, spacing, end location, bolt count, and plate washers. I look at the work area for approved impalement protection and stable forms. I confirm the inspection status, then I manage the concrete delivery clock. That sequence stays within the general B boundary. I am not replacing the engineer, geotechnical professional, inspector, or approved plans. I am making sure the physical work, documentation, trade coordination, and timing agree before an irreversible operation begins. This is a testable concept based on the published CSLB study outline because it combines concrete, earthwork, field inspection, code compliance, and safety. The best memory connection is not a single isolated number. It is the order of control. Support, moisture, steel, anchorage, safety, inspection, then placement. I made an audio practice quiz for this specific episode so you can test the same footing. Slab, vapor retarder, subbase, anchorage, safety, and sequencing decisions. It is audio-based. The questions are read aloud, and you answer by tapping, which works well when you are studying while driving, working, or on the go. Go to the description below this video. You will see a link that says Pass the CSLB. Tap it. It will take you straight there. Comment below with any questions about what I covered. Subscribe so I can help you stay on track through every episode until you get your license. I know this material has to fit around real work and real responsibilities, and I want each lesson to make that study time count.